So we talked about ionic compounds in the last segment. Now we're going to talk a little more about covalence and the difference between covalent interactions, the difference between ionic and covalent interactions. So switching to the tablet, the learning objectives for this segment are going to be describing the difference between ionic polar covalent and non-polar covalent bonds, and predict whether a bond will be ionic or covalent using the atomic electronegativities. So ionic and covalent bonds are quite different. We were just talking about sodium chloride and how it's a white solid. Its melting point is about 800 degrees. And magnesium oxide, which is held together even tighter, has an even higher melting point. So it's pretty hard to tear that apart. Hydrogen chloride, on the other hand, is a colorless gas whose melting point is minus 100 at room temperature. Its melting point is minus 105 Celsius. So it's actually, very different. The sodium chloride is just one big network of things stuck together. You don't really have one sodium bound with one chloride. You have a crystal of sodium chloride. Whereas hydrochloric acid, you literally do have one hydrogen and one chloride per molecule, and those molecules don't interact with each other that strongly. They can be pulled apart quite easily. So, as I'm sure you know, we're just reviewing here and putting it into context. For ionic bonds, you have an electron transfer from the usually something that's more metallic to something that is non-metallic. You get a cation and an anion, and they attract each other by covalent interactions. In contrast, for a covalent bond, you have sharing of the electrons. You have two electrons come together, and the nuclei are repelling each other, but the nuclei of one atom and the electron cloud of the other, and the electron cloud of one and the nuclei of the other are attractive, and then you have repulsion between the electron clouds. But so this is the electrostatic interactions, but what you can actually do is have the electrons start to share between the atoms. That there are, and the way to think about it mathematically is there are solutions to Schrodinger's equation where now you're not just dealing with multiple electrons, you're dealing with multiple nuclei as well. So when you have two electrons together, there are solutions to Schrodinger's equation, or there are in many cases solutions to Schrodinger's equation that are lower in energy, that involve electrons being delocalized between the two atoms. And so that's what the covalent bonds are. There's a sharing of these electrons. But if you're sharing electrons, that doesn't say you have to share them equally. If you have something like chlorine, Cl2, these, they're essentially identical atoms. And so the electrons will, of course, be shared equally. To the extent that they're shared very evenly between the two atoms. By symmetry, like you switch the two chlorines, you can't tell which is which. It has to be equally shared. And so there's no net imbalance of electrons on one side of the atom or the other. And so this is called a non-polar covalent interaction. The electrons are shared and there's no unequal sharing of the electrons. However, if you have something like hydrogen chloride, then the chlorine, it has a big nucleus. It's actually going to be pulling on those electrons a little bit more. The hydrogen has just got one proton in the nucleus. Chlorine's got a lot, and so it's pulling the electrons. It pulls the electrons away from the hydrogen. The side with the hydrogen on it, it becomes a little electron deficient. It's actually positive, and the side on the chlorine has a little bit more of an excess of electron. It's a little bit more negative. So you actually have a polarity in the molecule itself. As in contrast, if you have sodium chloride, you don't really have just two things of sodium chloride. But if you did isolate just two of them, then the electron would be essentially entirely on the chlorine and not on the sodium at all. And so these are very different. Depending on how the electron is shared, you'll have very different physical properties. As you can imagine, we'll talk more about it when we talk about phase behavior. The polar covalent one, they tend to attract each other a little more because they've got imbalances of positive and negatives, and so the positive negatives attract each other. Okay. So this has been sort of the extent to which things are polar covalent or non-polar covalent or ionic have been tabulated. So Linus Pauling, Nobel Prize winning chemist of about 100 years ago, took a lot of the information out there and sort of tabulated the extent that you have polar versus nonpolar character. And it was through this electronegativity value. Why fluorine ended up with 4, that was set as the maximum value. Why it's 4, I don't know. But this is essentially a measure of how much how much that atom pulls electrons away in a bond. So fluorine is the most electronegative. It's the one that most likes to hog the electron over on each side. And then the electronegativity goes down as you get heavier. As there's more shielding of those electrons as you go down. But this electron affinity has its roots in the same phenomenon as electronegativity, but they're different things. Electron affinity is a neutral atom pulling an electron essentially from vacuum that happens to be there. Electronegativity is within a single compound. And so these are average quantities over all the compounds that these are in. Okay, so electronegativity goes down as you go down the periodic table. It's the nonmetals tend to be more electronegative. Hydrogen, sort of a weird character there, as it usually is, because it only has 1 electron and one neutron. So electronegativity goes down in the same column, and along the same row, it generally goes up, although the transition metals are sort of weird, as they usually are. So for metals, it goes up. There's some weirdness here, and then for the non-metals, it'll go up as well. And again, the weirdness in the electronegativity has to do with complete shells, things like that. So, but I think the main trends to know are for the non-metals, it's strictly going down. Even for the metals, it goes down as you go as you go down the columns, and that generally it increases across the rows. And really, these right here are the things that are the most electronegative. Okay, so we've got electronegativities. We have sort of a tabulation of within a molecule how much it will pull the electron over to its side. Yes. So now we can actually look at these same compounds, and let's put numbers on them. Let's look at the differences in electronegativity and see what we get. So in this case, between chlorine and sodium, chlorine is 3.0, sodium is 0.9. Chlorine and hydrogen, 3.0 versus 2.1. Chlorine, it doesn't matter what they are. Clearly, they have the same electronegativities. And so generally, when you see something is over 2.0, you say it's mostly ionic. If you have something between 2 and 0.4, then it's considered generally a polar covalent bond. And if it's less than 0.4, it's non-polar covalent. Now this 0.4, some books use 0.5. It's really a vague thing. Like really polarity is more of a gradient, right? You can be exactly nonpolar. Cl2 is exactly nonpolar. You can be fully ionic. There's essentially no sharing. And then there's a whole continuum along the way. So exactly where the drawing line is sort of arbitrary. I would not be trying to catch you like, aha, no, it's actually polar covalent, not non-polar covalent because it's 0.5 instead of 0.4. That's sort of a meaningless sort of thing. It's really, we want to describe this gradation, and we divide them into general categories, things that behave more or less in a non-polar way, things that have sort of charge imbalance between one side and the other side of the molecule, and things that are purely ionic.